Hello and welcome to this latest version of the Explore Machine Learning program with the Google Developer Student Club at London School of Hygiene and Tropical Medicine and me, Gregory McGann. This is a really exciting episode of this lecture series because we're looking at natural language processing, which is, for many people, the hallmark of true machine learning. It's in fact the basis of or one of the bases of the infamous Turing test, which is the method of knowing whether a machine can fool a human, and it's generally seen as being done through language. So natural language processing is often seen as the holy grail of machine learning, if an artificial intelligence, rather. If a machine can have a general understanding of language and imitate humans within the margin of error, then that would be general intelligence having been achieved. And so despite being very, very far from that, and I think we'll discover over the course of this lecture, just how far we are from that, and just why we are so far, and why the course of learning has diverged slightly. We'll also have a look at some other stuff, but without further ado, let's look at the contents of the lecture. Okay, so what is natural language processing? I'll quickly explain that. What can natural language processing do? And then I'll give you an example in R with Sentiment R, which is a package, and then two examples in Python. So Python, I think, is more generally used for natural language processing just because it's a more at home with machine learning. That's a very debatable statement, but generally Python has been seen as more amenable to natural language processing. But we are going to start off with R because I know this community has a strong commitment to R, and so we'll start off with that using a very common, very simple package called Sentimenta or Sentiment R, which can do sentiment analysis, which we're about to discover is part of the equation. Okay, so what is natural language processing? Here's the technical definition. It's the branch of AI concerned with machine comprehension of human text and speech. It combines computational linguistics with statistical modeling. The first component of that is computational linguistics, which is the rule-based modeling of human language. The second component is statistical machine learning, deep learning, and it should say here probabilistic modeling as well of language. These components are both cooperating and competing. The reason I wrote that is because you can more or less summarize the history of artificial intelligence and natural language processing with an idea of these two sides, computational linguistics and statistical modeling, working together, but at the same time being very, very profoundly in competition with each other. And the early history of, I'll give you a whistle-stop tour of the history of natural language processing, which is that in the 1980s and 1990s, there was a lot of energy, especially around corporations such as IBM, around the possibility of creating, putting essentially all the rules that you would find in any dictionary into a model, and then having that model output language. So you could say you could input a command, and then by the genius of the computational power was just becoming available at that point. So this was kind of like the post-war period when Moore's law of ever increasing computational power was in full effect, or is becoming cheaper and more economical in size. And there was great hope that because language is fundamentally rules-based, you could simply have a gigantic sort of machine. You could have a programming script, however long it would be, with however many logical rules, and you'd be able to output language. And you'd also be able to conduct various logical tests on it to say, well, does this have a verb? Is it a sentence? Does it have a period? Is it a sentence? Does it have a semicolon? Is the semicolon used correctly? So there was a lot of hope for that it would become that this would be would solve the problem of NLP, and therefore you could pass the Turing test because you could create something that could output realistically human language. But there was that never came to fruition. And the truth is that language actually is rules-based, but it is so innovatively and dynamically rules-based, and with such incredible variety. But despite the computational powers available at that time, and even today, we do not have, we cannot perform the necessary calculations economically. Short of having a quantum computer, which may be possible in the near future, and in fact, if you're a user of Amazon Web Services, AWS, you'll know that on Amazon Web Services, there's actually a app which you can connect your operations to, which actually is seemingly connected to a quantum computer. It's called a bracket. Anyway, okay, so any questions so far? Does anyone have any kind of queries? Okay, good. Radio silence, that's what we like to hear. Okay, so that was the early history of machine learning, of NLP. So it was sort of like the failure of the rules-based system, which is essentially computational linguistics. So the computational social sciences had come together and tried to create this kind of something akin to a Council of Nicaea, where you just sort of codified all of language and tried to output something. And it really didn't succeed just because of the complexity of language, and it wasn't even progressing in a linear fashion. So even as computational power increased, natural language processing on this model did not increase in capacity. So it seemed like there was a sort of intractable problem, and translation was really the touchstone of this, because they couldn't get translation to work. I mean, translation should be the easiest thing because there's a dictionary and then you can just move it over, right? Didn't work. So we then had a sort of the second age of natural language processing was the dawn of big messy data. You've heard of big data, but you probably haven't heard of big messy data, because the real equation, the new modus operandi was, we're going to have loads and loads of information. We're going to put in lots into the machine, but it's not going to be perfectly ordered the way we'd like it to be, and so it's going to be messy in a sense. And we're essentially not even going to look for these rules, which would ascribe a kind of causation and provide a rationale. We're simply going to look at correlation in existing, for example, translation, and just copy and paste it over, and to see, we're going to mash it up and create some kind of probabilistic model where we can say there's a 60% chance it's this, because this is the evidence we have, and there's a 40% chance it's like this. And we're not going to speculate on exactly what the rules are underlying that. And this approach gave birth to Google Translate. And essentially what Google Translate did was, due to the volume of information crossing Google servers, it was simply able to track those correlations very efficiently on an unimaginable scale. So Google Translate is clearly an amazing tool, and it succeeded where, say, IBM failed. And so now we're very much in the frame of mind where the statistical modeling, the probabilistic modeling, which we now refer to, of course, as machine learning, and sort of the foundations of machine learning and deep learning, as being the dominant form of natural language processing. But there is still a computational linguistic element, because as we'll see today, we can still do a lot with basic rules, and we can still kind of it's still to an extent dependent upon a rudimentary foundation of basic rules. But never underestimate the extent to which these two sides are competing with each other. This is hardly a solved problem, and I think computational linguistics might be like sort of coming back a little bit, because now, because we want to think, there's more of a push for accountability in speech recognition, disinformation, etc., hate speech. We want to know why things are the case, where they came from. There has to be more accountability and transparency in the data science pipelines, and that is leading us to ascribe quasi rules-based modeling in order to do this evaluation, if that makes sense. Okay. That was a long explanation, but this is the foundation. This is both the history and the theoretical foundation. So the combination of computational linguistics and statistical modeling. Okay, what can natural language processing do? So these are 4 of the kind of examples that we have. There are many, many, many more. And there are as many uses of natural language processing as there are uses for human speech. So as you can see, there are nearly, there are simply uncountable, innumerable uses, but these are some of the most important ones. Information extraction is number 1. Of course, this is just the most basic one. This is where a machine will look for important information and simply extract it from a huge corpus of text. Very famously, quants do this in the stock market, and sometime in the Obama presidency, a quant algorithm was doing this information extraction, and it found that there was that 3 phrases were put together, which was White House, president, and bomb in the same sentence, and it immediately initiated a sell-off because it assumed this was took this as a red signal, and it was called the flash crash. There was a huge sell-off of stocks just as on the basis of this algorithmic trading, which was without accountability, without sufficient transparency and checks and balances, clearly autonomously trading on the basis of information extraction. So we're going to do some information extraction and some sentiment analysis. We're not going to do any language generation today or speech recognition, partly because that is a hugely more difficult task, and we're going to be doing some actual coding. But to achieve information extraction and sentiment analysis. Number 2, sentiment analysis. Well, I'll just explain the second one. These things are sentiment analysis anyway. Language generation. This is this is kind of like the holy grail. Can we take inputs and then output language, which is far harder than taking language and outputting some information about it. And then speech recognition, which is sort of incredibly more incomparably more difficult than text recognition, because everyone speaks language differently, and the idioms that we all have present a vector of uncertainty that is fiendishly complex and very, very hard to do in any sort of normal setting. Okay, so number 1, sentiment analysis. We want to extract some subjective qualities. So because it's subjective, what we're going to be relying on are dictionaries and sort of modalities. So these would be things like saying the word horrible is a negative word. So it's essentially like if you're familiar with coding at all, you have these. It's a fundamental tenet of coding is simply that you have these. You can make these dictionaries, and so you can match terms. And so with very limited coding, you can in effect do this sort of sentiment analysis if you can create a dictionary, which we're about to, or use rather. We're not going to create a dictionary this time, but we're going to use existing dictionaries. So let's do one in R. I'm going to stop sharing, and then I'm going to just do some quick sentiment analysis. Share screen. RStudio. Hopefully this is big enough font for you. Okay, so what we're going to do is we're going to use we're going to do sentiment analysis with the sentiment R package. One of the funny things now is that this is just an aside, but for anyone who's interested, Now, the reason why I write these comments is obviously for kind of like institutional memory. It's a good thing to do as a programmer, but now we have programs that conduct natural language processing on your comments and then anticipate your code. So it's like auto completion on texts. It is so fiendishly good, but unless you're an exceptionally gifted programmer, it's usually going to guess better than you would have written it. I know this from firsthand. There's a very good program called GitHub Copilot. GitHub is a massive repository of code, which we assume is being used as a sort of massive big data and big messy data input into GitHub Copilot, and then it can sort of guess what code is coming. So that is a very good example of text analysis. Except in this case, it's not natural language processing; it's code processing, which is in fact far easier because it's far more rules based, which is why these things are so effective. Okay, so let's install our packages. Sentimentar, whoops. Sentimentar. I've already loaded it, so I don't need to do this. I'm just showing for you for your sake. If you want to, you can go to here over to packages. If you see here on the right hand side, this is in the sort of like lower left, right. So this is RStudio. It's not R. So you have to go to rstudio.com, I think, and then you just download RStudio. So if you see here in the bottom right, you have packages. You have files, plots, and packages. You can actually just search in here Sentimentar. Oops, if I spell it right, which I won't. And then there you have it. Sentimentar, calculate text polarity sentiment. So polarity really will give away what we're doing today. It's a very good word, actually. But okay, let's do it our way first. Library sentiment. I can't spell sentimenta. It eludes me. Okay. So we've loaded the package. Now we'll just put in some text. So this really is the most simple thing we can do, but we're going to put in some text. Enter random text. Some text. I'm going to put it in a list, okay? So the way we're going to do this is that we're going to have like blocks, each sentence will be like an element. So that requires us to make a list. So if we were grabbing this on the internet, say, which we did in a previous tutorial, what we had to do was grab it and then split lines, which is a command, and then so each line would become an element. But we haven't done this time. We're just going to like manually enter it. So what should we write about? Let's write about Harry Potter novels. Harry Potter is a very good book series. That's our first item. That's our first sentence. Let's write another sentence. The books are very compelling. I'm putting in a, keep a note of this word, compelling, okay? Very compelling, emotional, and accessible. That's our second sentence. Our third sentence would be the author is a great writer. And then fourth sentence, the books are a waste of time and terrible. So what I've done there is I've just completed that. So what I did here was I've just created a variable called subtext, and it's just a list of these sentences. Okay. So you can see how easy that was. Variable, list, and then speech marks, and then each sentence. And now we can actually start to do some sentiment, which I still can't spell, moronically. Sentiment analysis. Let's do a very simple one first, which is just sentiment. And if you see here's the documentation on it. which is that sentiment text.var, so text variable. And then there are all these other things you can add, which we're not going to. But you can kind of filter for different things. But we're just going to put in our variable and see what it outputs. So you can already see that it has some useful information. It's done a little word count for us, which is nice. But what we really want to see is this. Which is the sentiment. So it's ascribing a value from 1 to -1, which is what it basically means by polarity. So polar 2, so it's between these two, -1 and 1. And less than 0 is negative, and up to 1 is positive. So you can see that it's kind of like the first sentence was okay, quite positive. It's closer to 0 than 1. The second sentence, which was, let's remind ourselves, the books are very compelling, emotional, and accessible. That's more positive. That's like 0.64, so that's 64% positive. It's not really a percentage, by the way, that's misleading. But the second one, the author is a great writer. That, it seems to be saying, is not as positive. That could be because it's less coherent if you have other items, but we can dig into that. And the final sentence is, the books are a waste of time and terrible. And so we've actually got -0.5. So this is you can see it's a horrible score. So we've already done something quite useful. So if for example you're a newspaper editor, a newspaper editor, and you're kind of concerned that you have 100 articles to read today, and it's already 11 p.m. and all the copy is due at midnight, and you don't have a hope in hell of reading all of this stuff, and you think you read it, but you're tired, so you don't know, and you think there could be like a negative thing in it or something. I don't know. Like, you run this, and then you can find sentence by sentence. Seems like there's a strangely negative sentence there, and you can go and check it. That's just one example. But let's do some more. So let's actually extract some keywords, because that's our next step. We want to know what's going on here. So let's extract. As you can see here, we've got some options: extract emotion terms, extract profanity terms, extract sentiment terms is what we're going to do, because we just wanted to sort of see what's going on. But we could go profanity. Could go with emotion. We're going to go with extract sentiment terms. And if you see here, we've got some quite interesting results. So it's picked up positive words: good, compelling, accessible, and great. It's picked up the two negative words: waste and terrible. I wonder if we can add something that will be kind of ambiguous. So why don't we put in something like why don't we put in, is a great and I want to say sly, or like something like it's a bit more dubious, and sly, right? You know, like sort of cunning. So let's just redo that with this new text. Sly is negative, you see. So now if we were to do the same thing of the original, just get the scores, you find that this one, the third sentence, is now kind of neutral. 0. It's exactly on 0. So you can see this is actually quite useful in just kind of if you want to find out something like I'm a political candidate and I have to read 100 different articles about myself. Are they positive or negative? I can't read them all. But I can put it through this algorithm, which we could easily put into a pipeline, and just and then we could find the most complementary one, and then we could anticipate the most negative one, and say, well, these people are all liars. They hate me. So anyway, this is a really useful thing to have at your fingertips. As you can see, we've written this in like 3 lines of code. Anyway, let's get back to our slides, because this is just a little quick and dirty little example. Any comments so far? Okay. We're going to share screen again, just on the old presentation, our old friend in the presentation. Okay. So we've done that. You know, just for good measure, I always record my programming segments and put them in the presentation as well as actually doing them live, just in case it won't share or something. And also because this is machine learning, so your computer will often get bogged down. It's a real thing, by the way. That I've had to buy a new computer because my computer currently won't do all my deep learning stuff. A lot of people build their own computers. That's going to put you back £5,000. Okay, so our next thing is information extraction. We've already done this essentially. This is different from sentiment analysis. Information extraction is basically neutral. Sentiment analysis is rooted in subjectivity, and so it requires quite a robust dictionary. And by robust, I mean accessible. I mean that you can read it and say, well, I don't agree that sly is a negative word. I think it's a neutral word. It is a negative word, but you get what I'm saying. So when it comes to sentiment analysis, you want to really have a firm grasp of the dictionary underpinning it. Information extraction is much more neutral, and you can do it in a way that won't be affected by these subjectivities. And that's why information extraction is predominantly the one used in kind of algorithmic trading, because you don't really want to have these kind of complicated subjectivities. So one of the basic, and of course, information extraction and sentiment analysis are rarely differentiated. Only when we're doing this pedagogy will they be separated. But let's just say they're separated. Okay, so information extraction, it analyzes patterns in text using trained models or functions. And the computational difficulty rises exponentially with abstraction. So what does this mean? It means at the very simplest level, you might just be searching for one word. That's what Microsoft Word does when you put in something in the search bar. It just searches the whole thing and it finds a word. Let's suppose you want to do something a bit more complex. You want to find 2 words together, which is what we're going to do later. That's much more difficult because you have to search it, you have to find the word, and then you have to conditionally look at the word and then look at the word next to it. So that's an extra step. And that requires a little bit more programming. And then you're going to do then the level of abstraction would be something like, does this, what does this say about X? You know, what does this, so we have to take out the information and recombine it. We have to look at the context closely. And what you'll quickly find is that context is, you can map as a graph. And that's what we're going to do at the very end of this lecture. And unfortunately, the fact about graphs, which most people refer to as networks, is that the computational difficulty of doing them is immense. And probabilistically, the number of different outcomes rises at such a rate with a network of this nature. So what we're going to look at is a co-occurrence graph, which is basically to say which words are next to each other, which words are in the same sentence as each other, which words are in the same paragraph as each other, how far away are they from each other, and in what context, what other context, what other words are there. If a word contains 10, if you know, it's like a sentence contains 10 words, look at all the relationships between those words. So look at each word in turn and then the relationships to all the other words. Check it against a dictionary of all words, and then continue to do that for the whole corpus. That is exceptionally difficult. That's why we're not going to do it in programming. We're going to look at someone who's done it in programming and look what they got. But what we are going to do is a quick example of basic information extraction in Python. So I'm going to stop sharing again, and we're going to go over to Google Colab. Google Colab is, I think, the best way of sharing code because it's not based on your own computer. And as a result of that, you don't have to worry about kind of version issue problems or, version problems or, you know, various other things that are reliant on your own state of your own CPU and stuff like that. Of course, it uses your CPU, but you get what I'm saying. Like, if you use the alternative to using Google Colabs is Jupyter Notebooks, and Jupyter Notebooks uses your directories, your folders. So unless you can replicate your folders, it's very hard for someone else to do it. Of course, if you go to GitHub, you can just download whole folders. But I don't expect any of you to do that. I don't. So it's bad practice. Okay, stop sharing. Okay, let's go to Google Colab. Let's just load it up. The computer's being a little bit slow. Chrome tab. Let's just refresh this. Okie dokie. So we're going to start off with importing our packages. They're not called packages in Python, but never mind. And what we're going to be relying on this time is a package called Spacey. It's actually spelt online like capital C from a German company called Explosion. They do really great work, so check them out. Just giving them a shout out. So we're just importing Spacey. And by the way, if you want to do is you just type it in, and then you press text here. Code, and then you just press this play, or you press Command Enter to make the code run. And then okay, so we've got our packages. Now what we need to begin doing is we're going to build our sort of our function. You don't have to worry too much about this. This is mainly just like as a tool for you to think about. So worry about the inputs. Don't worry too much about how exactly we're doing it. So Spacey dot blank, and we're just going to specify language. So this is just kind of like this is just getting the basic information that Spacey provides us about English language. So it's a sort of dictionary of English language and its properties. And NLP obviously is just what I've called it. You could call it anything, but obviously NLP is like natural language processing. And then we're going to create the doc object. So doc object is rather like what we just made in terms of the variable some text. But in this case, it's kind of processing it first, which is why this is slightly more advanced. So whereas before we had like some text and then a variable is just some list. It's just a list of sentences, a list of strings. This is actually going to process it first in some way. So we're going to actually use NLP as a function. What we've just done is the thing we've just made is a function. Don't worry too much about this, but so doc you don't have to, you can call it anything, but I'm going to call it document equals NLP. And then what should we put in? Hello world. It is. If I could spell my own name, that'd be useful, wouldn't it? It's Greg. Okay. There we go. So we just created that doc variable, and remember we've used NLP as a function, so it's already gone for. It's already said this is the English language. We're putting it through the spacey kind of filter. Now let's just have a look at it a little bit. So let's see how we can treat it, because now it will be a trying to understand a doc object. So it will be what it does is it kind of turns it into a list. You can interrogate it as a list, is what I'm saying. So let's iterate over this list, over the list. Tokens. We call them tokens. I'll show you what that means in a second. In the doc. For token in, oops, yeah, token in doc. And we're gonna have to hope my computer can handle this, because it is old, and this is a bit difficult. Okay, so as you can see here, this is the list. What is interesting about this is that it's put apostrophe and s together, but it's put comma on its own. This is very idiosyncratic of the English language, because the apostrophe s has been taken as it's kind of is a distinct thing, as opposed to just apostrophe. I'm no great shakes at like punctuation, so yeah, even so, I'm giving you my layman's view of punctuation, but this is what's in your doc. This is what's in this. So in other words, this is what NLP has done to this. Okay. Let's go to the next thing. We can take certain parts of the doc if we want to, and we just use a standard Python sort of slice for that. Python slices are just like, or in a list of things, you take certain parts of the list. So in this case, we're just going to take like the slice. I think in Spacey they call it span, but you don't have to call it span. They just call it that in their documentation. You don't have to remember that. We're going to call it span as well, for some reason. And let's actually just print that just to make sure we can just print span and not text, but yeah. So what you can see here is the values between 1 and 3, but not including 3. So these are the values. And by the way, programming counts from 0. This is a curious thing about programming. I'm sure you know this, but it counts from 0. So hello is 0, and 1 is world, and 2 is the comma, and 3 it doesn't count. So yeah, I know it's bizarre, but what? So if we wanted to include it, then we'd have to do it up to 4, right? So then it counts the second, third, and fourth items. I don't know, weird, but right. Let's do some more exciting things, because this is just like showing you the properties of the doc object. And remember, the doc object is just that we've taken some text and we've rammed it through Spacey, which is the package we've downloaded, and then we've got doc. So doc is just something we can interrogate more easily. Believe me, this is the hardest thing in NLP, is having something you can interrogate, because usually text is just very, very hard to get at. Very hard to, you get it from the internet, it's in some funny form. How do you break it down? Do you turn it into an array? Do you turn it into numbers? So having something already which has broken it down for you and which you can interrogate is really the holy grail. But let's do something more advanced. Let's test for punctuation. So let's just print. Let's do proper documentation. Test for punctuation. So this is an important thing in all natural language processing. What is punctuation? What isn't? And you know, it's not going to surprise you that Space is going to get this one right, because it's a pretty easy thing to do. Is punct is the function. I'm just putting it in a form here where it will output something that is intelligible. You don't need this print function. I'm just putting it like that so you can kind of see what's happening. Token is, you can see all the options here. Is currency, that's another important one. Is bracket, that's very important for coding, knowing where brackets are. But today we just want, oh, and is quote, it's very, very important. That's a really, really useful one. But anyway, let's do is punct for now. Is punct for token in doc. So you can kind of see what's going on here. And by the way, I hope this is, you can kind of, it's big enough. The font is big enough. I'm going to like make it a little bit bigger. So you can see, yeah, false, false, true, false, 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 true. So let's just look at the hello world, punctuation. It is Greg. Now, what's interesting here is it has not counted apostrophe S. So you're going to have to learn that punctuation in NLP is slightly different to punctuation in real life. And why is that? It's a shortcut to allow us to interpret things more easily. So it's decided that it's like apostrophe S is not punctuation. Comma is, and exclamation mark is. So getting accustomed to this sort of thing is really important for your NLP journey. Let's do one other thing. Let's test for numbers. This is an interesting one because numbers are. So I'm just moving my computer a little bit. Numbers come in lots of different forms. So what we're actually going to do for test for resembling numbers. The like functions are the real value of this package, because like is not just a binary Boolean yes or no, true or false. Like is it is going to output as a Boolean, but what it's going to do is it's going to have to check an enormously greater number of things. Is it written is it written in letters like free, THREE, or is it written in some other way? Is it, I don't know, etc. So what we're going to do is just print again. So I want to keep it in this format. Like num. Oops. Token dot, and remember the token is each element inside the doc, right? So it's so what we've got here in number 4, if you just observe this, these are the tokens. So this is what we call the elements. In R we call them elements. In here we call them tokens. But search me as to why. They just do it to annoy me pretty clearly. But yeah, they call them tokens. So these are all tokens. So what I'm saying here is token. So check each one. Token dot like num. And then we're doing the kind of loop again. So for token in doc. Okay, we don't have any numbers this time. Okay, it's Greg. I am 29. Let's put that in. It's not true, by the way. I'm 19. Anyway, so now you can see that it's outputted true for 29. Okay. And there are other really useful ones which are used in industry, like test for email similarity. So is it like an email? Similarity. Print like email. Oops. So the same format as we're saying, like token for each one, and then like email. Another one here is like URL. So this is a very useful one. Is it like a URL? Like email for token in doc. So again, what we're doing here is this is a for loop, so it's just going through each one in turn. And what does it say? Nothing's like an email. Surprise, surprise. Let's just put in some emails. Let's just put in some random sort of emails. GregoryMcGann@gmail.com. This isn't actually my real Gmail. GregoryMcGann@gmail.com. Mr. Someone at yahoo.co.uk. Then just some random nonsense. And then let's test this again. True, true, false. So this would be very useful for enter your email here, and then if it's like not an email, it will reject it. So this is what's being done on things like Google Forms when it says enter your email, and then it says enter a valid email. Of course, Google doesn't know all the email formats in the world. It's just using an equation it's just using an algorithm like this. Okay, so we've done something quite cool here. We've done some basic information extraction, and we've done some probabilistic information extractions. We've said, is it like a number? Is it like an email? So what would have done here is it would have sort of checked, is this similar to, and what probability is ascribed to it? It's given us a Boolean, so false or true, because that's what's most useful in industry. But we could actually have found a way to ascribe a kind of like 75% probability that it's an email. But we've done a little, we've got some basic information extraction, and we've added a little bit more complexity. But let's go to the next stage, because there's, as I was saying, the computational complexity of this task really lies in the context. So looking at other words in the same sentence, in the same paragraph. So what we're going to do is we're going to open a new notebook. And we're going to call this one GDSC spacey percent. Because what we're going to do is we're going to try and look, we're going to look for percentages in a document. In a document. Why is this more difficult? Because percentages are contextual. You don't just want any number. You want a number that is next to a percent sign. So we have to write a little bit more complex code here, and and of course the relevance of this is that in industry, this is something you would do all the time. You won't just be looking for one thing. You can easily do that in Microsoft Word. You will be looking for things in context of other things. And then at the very end of this tutorial, I'll show you the logical end of this rising complexity. Okay, let's start off with what we did before. So we're just importing Spacey, if I can spell it correctly, which I can't. Import Spacey. Take a quick breather. Okay, so we're going to do pretty much the exact same thing we did before. We're going to create a NLP method function, sorry, not a method. Just with a blank, and then set it to English language. So we've got our weapons. Don't have to worry too much about this. Now we just as before, we create our doc, which is what we can. So what we want to do now is just create something that is we can interrogate, but it's in a form that we can interrogate, and that's our doc. So doc equals NLP, which we just created, and then we're going to enter some text. So what should we put? Did you know that 60% of all statistics are made up, and that 50% are misleading in other ways? That is a central data joke of statistics, but we'll use that. We have two percentages here. But you know what might be useful is if we said that in 2022, we added that as well. Why? Because now there's a number that's not a percentage. And also we could do another operation here, which was to say it has to be between 100 and 0, otherwise it's not a percentage. But that would be like a sort of validity check. So how are we going to do this? We're going to have to loop over every token in the document, which is basically just to say we're going to look at every token individually, every part individually. And then once we've done that, we'll check whether it's a number. So we'll use it what we already looked at, which is it like a number? That's a function, like underscore num. And then once we've done that, we'll check, is it next to a percent sign? And only then will we record, will we return the number. Okay, so for token in doc, so all we're doing here, this is our for loop. Okay, so this is Python programming, so we'll do for. You see, because it's purple, it's a reserved term. For token for each part of this, each word here, well, no, not even a word, but each piece of punctuation or word in the doc, which is the whole thing, colon. So we're starting now to do the loop. If token dot like num. So what we're doing, okay, let me put some documentation here because it'll make it easier. So start off by step 1. Iterate through the entire doc, the sentence in this case. Step 2, check if a token is a number. So if token dot like num is like a number, so we're using a bit broad, is a bit broader here. Is it like a number? If token.LikeNum we need to we set up a variable which is, oops, if I can get it correct. Next token equals doc dot token dot I plus 1. So breaking this down, step 3, if I can spell step. Step 3, we need to find the next token and check. We just need to find the next token. In this one we're not even checking anything. We're just finding the next token, which is to say, find token adjacent to selected if num. And what we've done here is we've ascribed, this is, Python is quite a succinct language. So whereas in something like JavaScript, it has to be more explicit. In this case, we're simply implicitly saying that I is the iteration. So it's this particular token. It's this particular one that we've reached in the steps. And then plus 1. So it's whichever one it is, and then the next one. So now we need to test to see whether next token actually is a percentage sign. Dot text, and this is why we need text, by the way, because previously we could just like report doc, and it will just show us the whole thing. Text is specifically the text of it. So it feels like a technical distinction, but when you're testing for strict equality, which is what we're going to do with the double equal sign here, you want to use text. So just like, is the text the same as the percent sign? So this is step 4. Step 4, test if next dot token, which is what we've just created in step 3, is a percent. If that is a thing, then now we can finally do step 5, which is return the output, return the number. Number. Print. Oops, I'm always let down by my spelling. Damn you, English language. Colon. This is just arbitrary, but I'm just making sure the output, you can see it in a nice way. Percentage token.text. And let's run this. Hopefully it works. Yep. So now we can see here that it successfully found the two percentages. Percentage found 60, percentage found 50. It did not report 2022 because that did not have a percentage sign next to it. So you can see how in a way this is efficient, but at the same time, how much more complicated it can get when you need to add conditionals. You're not just searching for something, you're searching for something if. You're searching for something in context. So if you imagine that I also wanted to check whether it was actually within 0 and 100, that would be another line of code. If I wanted to check whether it added up to 100 within a sentence, that would be another line of code, but maybe even several lines of code. But within 5 lines of code, you can check whether the neighbor is a certain thing. So we could have actually tested here: is it like punctuation. So then we could be like, is it number next to punctuation? I don't know why you'd want to do that, but you get what I'm saying. Like that's the next step up of natural language processing is contextual, or in the parlance, co-occurrence. Okay, so we're an hour in, and I hope this has been useful. That's the end of our programming. But let's look quickly at the very, very end of this, which is an amazingly complex thing, which will take a lot of machine learning. We're going to take a lot of computational capacity, more than I have on my desktop or laptop, but which we can look at in someone else's time. So let's look at it. Getting back to our friend the slides. This is just what we just did. So this is what we're going to look at. More advanced analysis. Co-occurrence graphing, really important co-occurrence graph. Well, complicated co-occurrence graphs. So what we're going to do here is we're going to look at this text. This is from the United Nations. This is talking about democracy. And what we're going to do is we're going to ask some simple questions. Which words occur most frequently next to which other words? How far away are they from those other words? Where are they relationally to each other? That's all we're going to ask. That's just the equip for each. If you imagine what we just did, we're going to iterate over this document, over each word, over each, in this case word, we're going to discount punctuation over each word and just simply ask that question. For each word, look at each other word and say, how close is it? How often does it occur? And we're going to use a very ingenious tool called Infranodus, or someone else has used it. Well, I've used it in this case, and I'm just filming the results. But let's look at the results. Have this text in your mind. Think about how difficult that would be. Each word, you have to look at every other word in relation to it, and then you move on to the second word and you do it again. Of course, it will become less complex each time you do it because you'll already have exhausted some options, but nevertheless, very difficult. So let's enter that text here, which is the same text, and now we're going to graph it. This is what you're left with. Democracy is the most prevalent word. It's most often connected to universal, base, nation, and those are its main connections, and development. Here's a circular version of that. You can see each node or each word, which one is most connected to, and it's only showing the most prominent words. But let's return now to its standard form. And you can see immediately how interesting this can be for someone who doesn't want to view something in a linear fashion. So let's do a thought experiment now. Let's actually take out these words and see what the graph would look like without them. This is important because then you can actually see, you can dynamically model topics. So let's remove those ones and see what's left. How do these other topics relate to each other with democracy abstracted? You can see it's a very different picture. Base is emerging as very important here. It's actually the kind of center of this new graph. So what you can see is that, yes, we started off with, obviously democracy is important. The paragraph is about democracy. But by taking out democracy, we can see underlying connections. In this case, base. Why is base important? Clearly, the author was using the word base in this text in a way that connected their text, in a way that connected the whole of the paragraphs. And this is very important for real meaningful analysis of language, understanding the underlying connections and implicit connections. This takes a lot of computational power, and this is not something that you can do locally, probably. But there are ways to do co-occurrence graphs locally, and those sort of the tutorials for this programming do exist online. But they're in an early stage because this is the cutting edge, and I think a lot of academic disciplines are going to be rewritten around this sort of analysis. But it will always rely on a certain level of both subjectivity and initial fundamental work on dictionaries, etc. Okay, well, I hope this has been interesting, and I hope you can see the potential of natural language processing, how far it's come, how far it still has to go, and just how exciting a field it is. Okay, thanks, guys. Let's leave it there. Questions after I turn off the recording.